Alright guys, we're going to jump into our video on the cycling of matter. A lot of information here, a lot really dense. There's a lot of graphics and stuff. And so I highly recommend that you pull some graphics out of your textbook copies that are on Edmodo, or that you grab some stuff from online that will really help you to dive in a little bit clearer than you might be able to see in the video at all points. So we're going to start off our video. Talking about something that honestly you probably learned way back in elementary school. We're going to talk about the hydrologic cycle. Now in elementary school you didn't call it the hydrologic cycle, you called it the water cycle. And so at its basics, there's a real, sort of simple system of what's going on. We've got evaporation going on. We've got condensation, which it doesn't say in this little slide here, but condensation going on in the clouds, and then that leads to precipitation, where that rain comes back to the land. Now that's going to be true for us as well in APES, but of course we've got things that are a little bit more complicated. So we're going to consider a little bit about what's going on with some of the water in a few particular places. So first off, what I want you to notice in the slide here is that when the precipitation comes down, the water goes to several different places. So we've got overland runoff, okay, of the water. That's going to go to streams and rivers. That's eventually going to flow out into lakes and oceans. A lot of that water is going to seep down through the land by a process called infiltration, and sometimes you'll hear it called percolation. That works as well. And that water is going to go down to the water table, and for most of us, that's what we're going to end up drinking a lot of times, is we're drinking from underground aquifers that come about through this infiltration and percolation process. Now, that's going to lead to that water flowing out. So that water is going to get pulled out by us in many cases, of course, but in a lot of cases also, it's going to flow out to the ocean eventually, or into some sort of lake or some large body of water. And from there, we're going to get that big path of evaporation. But what also is important is that that evaporation that we're talking about happens in a few ways other than just the simple evaporation off of the lake. So let's break down just a little bit the process of evaporation. So one of the biggest ones that's important for us is something called evapotranspiration. If I could spell, it would help. Okay, evapotranspiration. And so we're kind of slamming two words together here, evaporation and transpiration. If you recall, transpiration is where plants are giving off water. And so evapotranspiration then is the water that the plants are going to give up through their processes of cellular respiration, and that's going to go up into the atmosphere. So we've got that. We've got some evaporation from, of course, as we mentioned before, from lakes, streams, okay, ocean. We've got even from glaciers and stuff. We get some sublimation and stuff. And then, of course, we also get some just from the ground itself. And so that's the essential points of our hydrologic cycle for us, is that we've got a cycle going on, and this is going to be sort of the path for all the stuff that we're talking about, is that there's some sort of cycle, involves a lot of the land, and of course in this case the atmosphere as well. And what really is going to be key to us in APES class is knowing the essential cycle, yes, but then knowing all of the side stuff as well. That's where we really get into the meat of what really affects things. So one of the things that's what we're going to cover for each of these cycles that we do also is, how do humans affect these cycles? Like, what do we do that causes change in these cycles? So for the hydrologic cycle, or the water cycle, the first thing is obviously we're going to take a lot of that fresh water out. We need it for drinking, we need it to irrigate crops, all of those things. And so that's going to affect the amount of fresh water that's readily available to evaporate and then condense and come back as precipitation. When we clear vegetation, and I'll go ahead and pop up the next one, or we drain wetlands, we're drastically affecting the cycle, because a lot of water gets stored in the wetlands. And so when we drain the wetlands and, say, put agriculture on it, like where I grew up in Florida, that's obviously a lot of Florida sort of drained wetlands, drained swamps, and then paved over, or has fields over it, or groves over it, or whatever. That has a pretty drastic effect, because then there's not as much availability for the land to store that water. And what they've discovered in the past few decades is they get a lot of flooding in those areas now, because they drained out those wetlands and tried to use them for a use that ecologically wasn't originally there. When we clear vegetation from the land, we saw this in the Haiti video, that when we cut down trees and we clear vegetation, that leads to a lot more runoff than we would normally have, because there's no trees or no crops there. The soil washes away, and so there's just nothing there really to hold the water in and let it soak in and let it go through that infiltration and percolation process. And then, of course, all of that is exacerbated even more when we're paving over stuff with roads and building buildings. And again, not to make a moral judgment and say that these things are bad. I mean, these things are sort of essential and necessary parts of human civilization. But at the same time, the vast amount of it means that, say, in downtown Knoxville, all that rain that might hit during a rainstorm, the vast bulk of it isn't going to be able to penetrate into the ground very well. It's going to have to go off into our stormwater system, and of course that's going to put it into the rivers and stuff, which is still going to go somewhere. But remember, it's getting pollutants off of the road and stuff, and all of that stuff is going to go with it into all of our lakes and streams, and that's going to affect water quality, and we'll talk about that later in the year also. So our next big cycle is the carbon cycle. Now, the carbon cycle essentially has two really main and big points to it, and that is that we've got photosynthesis. So the carbon cycle has two really main points to it. The first of those is photosynthesis. Okay, that obviously is going to be key because that takes in CO2. Okay, or that's the carbon. Most of what we're talking about in the carbon cycle is carbon dioxide. So photosynthesis is going to take in the CO2, and then respiration, which of course is the reason that we need the nutrients. We take the nutrients and then we turn the nutrients into energy through the process of cellular respiration. Remember, we're not talking about just breathing. We're talking about cellular respiration, where we break down nutrients and then we're going to then kick off or give off CO2. Okay, so you got two processes that really are at the heart of the carbon cycle, and really they're kind of a cycle in and of themselves. And so, like, if you look here in the middle, there's one cycle just by itself. If we're talking about, in that case, we're talking about oceanic cycling of carbon dioxide. And so, in that case right there, that is a complete cycle. Now, on the land, the same basic principle applies, that we've got photosynthesis occurring. Okay, plants, trees, all that stuff, that it's all pulling in. And remember that we're not just talking about plants that we can see, but of course there's a lot of microscopic stuff, phytoplankton, all that stuff, be a little bit more oceanic then. But plants are pulling in CO2 for photosynthetic processes. They're going to store the carbon as nutrients, store it as part of their bodies. So those are, remember, those are the producers, if we're talking about our ecological chains here. The consumers, okay, then are going to eat those. And then as the consumers die off, or as they excrete waste products from their body, that's going to put more carbon back into the system. Okay, and of course, as they consume, so like as the consumers consume the producers, and then their cells are undergoing cellular respiration, they're breathing out CO2 back into the atmosphere. Okay, and so that's this part over here. Humans and animals are respiring, we're putting stuff back in. So some of the carbon, of course, as we're buried, or as our waste products go out, that gets down into the soil, that becomes organic matter. Over the course of millions of years, that carbon can get compacted down and become fossilized carbon, which would be the case of fossil fuels like natural gas, oil, coal, all those things. The same thing is going to be true here in the ocean, that a lot of the oceanic organisms, phytoplankton is sort of the start of that chain, going to pull in the CO2. Other organisms are going to eat them. They're going to respire and give off CO2. Even though we don't think sometimes of oceanic organisms as giving off CO2, they do. They have a normal respiration process. It's just not in the form of gas phase. It's dissolved oxygen, dissolved CO2, all of those things. And then, of course, as they die off, a lot of that is not going back into the atmosphere, of course. It's going to go down and sink down to the ocean bottom. It's going to become sediments. And again, as with the stuff that's on the land, it can get compacted down and become fossil fuels. Okay, and so then there's some other ways that you sort of see here on the graph that are ways that humans are going to affect this. So a couple of the biggest ways that humans are going to affect this process is that we're going to extract fossil fuels, and then of course we're going to burn those fossil fuels. That puts an enormous amount of CO2 back into the atmosphere, because fossil fuels are intensely carbon rich. In fact, that's why we like them so much, because they make, since they're hydrocarbons, they make really good things to burn. They're really good fuels. We get a lot of energy out of them. But what that does mean is that when we do burn them and they turn back into CO2, that gaseous CO2 that was in a really compact form now is all out in the atmosphere, and so that adds an enormous amount of carbon dioxide to the atmosphere. Okay, and that's one of we'll talk later in the year about the greenhouse effect and human effects on it and stuff like that. And that's, of course, one of the big ones right there. Just to jump back to the slide a little bit here, don't forget, of course, plants respire. We always think like, oh, no, plants are always just taking in CO2. And they do take in CO2, but remember, they respire as well, so they're kicking off some degree of CO2 as well. And then, of course, we've got things like if we cut down trees. In this picture, they've got it burning, but it doesn't even have to be burning. We could be cutting down trees, and again, they're big carbon sinks. And so once those are dead and no longer pulling in carbon actively, then that means that a lot of that carbon that could have gone into their bodies is now back out in the atmosphere and is free carbon dioxide. Okay, so with the next few here, we're going to jump into what we call macronutrients. These are things that all living organisms need, and we're not going to talk about all of them. We're just going to hit the three big ones. But these are elements that every living organism needs in order to survive, and these things cycle to some degree too. So the first one is the nitrogen cycle. And you see this diagram. This actually, I was going to say it looks complicated, but to be honest, to me, this is a lot easier to read than those last couple were. So the nitrogen cycle is going to start with nitrogen in the atmosphere. If you recall that nitrogen is actually about 78% of the atmosphere, okay? And so you're like, well, there's a lot of nitrogen there, which there is. The problem, of course, is that nitrogen in its N2 state, okay, is pretty unreactive chemically. I mean, it doesn't like to really react with anything. In fact, they fill a lot of containers just with nitrogen for that fact that they know that it's not going to react with stuff, unlike, say, oxygen, which is highly reactive. Okay, so a lot of nitrogen in the atmosphere. So here's the trick to the nitrogen cycle. What makes the nitrogen cycle so difficult is that since nitrogen is unreactive, there has to be some way to get it into the soil. Like organisms need nitrogen in their bodies. It's an enormous component of DNA. Their nucleic acids, they have nitrogenous bases in them. That's nitrogen, and so we have to have that. Amino acids, the amino part is nitrogen, and so living organisms have to have nitrogen, but it doesn't come readily out of the atmosphere for us. And in fact, plants can't even pull it out of the atmosphere. Okay? And so what has to happen here then is that we have these little things called nitrogen-fixing bacteria, and they do a process called nitrogen fixation. Super highly important process biologically to all life on the planet is that these nitrogen-fixing bacteria, basically, they're going to pull N2 out of the atmosphere, and they're going to perform chemical reaction on it, and that is going to turn it into ammonia, and then that ammonia is actually pretty easily converted into ammonium, NH4+, and then that is the stuff that is, with a little bit more work, is going to be able for plants to work. And so you got nitrogen-fixing bacteria are going to turn the atmospheric nitrogen into ammonia. And then we have what we call nitrification, or nitrifying bacteria. They're going to take that ammonium and turn it into nitrates. Now, nitrates are what plants actually like. Fortunately, it's a little bit easier to do the step from ammonia to nitrates than it is to get from N2 to NH4. Okay, a lot of chemical talk there. I know, I can't help it. I'm a chemistry teacher. I like that stuff. So once it gets into nitrate form, that's when the plants can use it. And so that's when you see this next stage here in the path here, this assimilation. This is when the plants can take it in. The plants, the roots of the plants are going to pull those nitrates in. They're going to use the nitrates to build all of their proteins, amino acids. They're going to use in their DNA and all that stuff. And then, of course, that's how the higher organisms up the trophic levels get it. The plants pull it in. The producers pull it in from the soil. And then the consumers are going to consume the producers, and that's how they're going to get their nitrogen. And so what's always amazed me, one of these big awesomenesses about science and biology particularly, is just this step here. I mean, that we have to have nitrogen-fixing bacteria in order for this to work, or we wouldn't get any of this nitrogen because there's not really much other way to pull it out of the atmosphere. Now, there are minor ways, like lightning strikes and stuff actually will take some of the atmospheric nitrogen and turn it into ammonium or turn it into nitrates. But of course, that's not enough to sustain any large amount of life. It might be enough for a small amount, but certainly not the level of life that we have on the biosphere. So, how do humans affect this? Well, there's a lot of different ways here. So, a lot of nitrogen monoxide added to the atmosphere by burning fuels at high temperatures, which of course is what we do, particularly with jet engines and stuff. They're going to add a lot of that. That's going to lead to stuff like acid rain, one of the ways of acid rain. There's a lot of nitrous oxide that is released, N2O, that's going to be released from fertilizer. That's going to get into the atmosphere and attack the stratospheric ozone. Now, it's not the fertilizer itself. What happens is there's actually anaerobic bacteria that when the fertilizer is sort of clumped up and is keeping oxygen out, those anaerobic bacteria are going to make this nitrous oxide. So it's not just like throwing some fertilizer on your lawn necessarily does this, but it's the big piles of it and stuff. Of course, when we destroy any ecosystems, a lot of that nitrogen is going to go back into the atmosphere, and so then we have that problem again that it's back as N2, and we have to be able to pull that back somehow, nitrogen fixation again. A lot of agricultural runoff. Remember, a lot of fertilizer that we use, we get a lot of runoff. That puts a lot of nitrates into the water, and nitrates, we'll see here in a second, along with phosphates, get a lot of those nutrients in the water. You get these huge overgrowths, these huge algal blooms that then cause all these big fish die-offs and stuff that we're going to get into a lot more later in the year. And then, of course, if we clear land, in a lot of places like the clear land, what they'll do is they'll cut down the trees and then they'll kind of burn the area out so that it will help to get rid of the stumps and all that. But, of course, what that does is it actually consumes a lot of the organic matter that's in the topsoil, and so that basically eliminates all of those nitrates in the topsoil. It actually makes it less fertile than it would have been before that sort of clear cutting and that burning it out. And the last little thing here, and this is a part of that last point, but irrigation itself actually get some of these nutrients out of the soil, because of course we think, well, we have to irrigate to get water to the crops, which we do, but irrigation also helps to wash the nitrates away. Nitrates are really soluble, and so they will wash away with the water and actually go out of the soil that way. Chemically speaking, nitrates incredibly easy to dissolve in water. So last couple of points. Last couple of cycles here. I'm going to run through these pretty quick because they're important, but they're not as important as those first three for us. The phosphorus cycle, what makes the phosphorus cycle different than the first three that we talked about is there's no atmospheric component here. If you look at this diagram, there's nothing going on in the air really. This is pretty much a completely terrestrial and marine-based cycle. Where do we get phosphates from? Again, phosphates are incredibly important to us for a couple of reasons. So phosphates are like the essential thing in, sorry, I'm having problems with my tablet, DNA, RNA. If you remember the structure of either of those nucleic acids, remember they have a phosphate backbone. Okay, that's the phosphorus here. And then, of course, the big molecule in biology that we all remember talking about hundreds of times is ATP, adenosine triphosphate. And, of course, that is its major component there also is phosphorus. Okay, and so phosphorus really important, another big macronutrient that living organisms need to have. So where does the phosphorus come from if there's not much of it in the atmosphere, which there isn't? Most of it's going to come from rocks. There's a lot of phosphate in rocks, and so for us to use it, we can mine it. Some places there's a lot of it in the soil from erosion and stuff. And then, of course, that helps to fertilize the soil, and that's another one of those macronutrients that's going to make the soil rich and allow producers to grow. The consumers can then consume, and then that's how we're going to get our phosphates that we need. And so that's sort of the main big part. That's the beginning part of the cycle, is that the phosphates are in the rocks. Okay, plants are going to take those up. Consumers are obviously going to eat those. And then, so where does the phosphate go from there? Well, as those producers, consumers die, they're going to redeposit phosphates back into the soil, either as topsoil or, like, say, if they're marine organisms and it's not going to go into the soil, it's going to get sedimented down at the bottom of the ocean or down at the bottom of a lake. And then over the course of millions of years, of course, that gets combined with other minerals. It's going to become new rock matter. The plates are going to shift, and some of that is going to come back up, and it's going to get re-eroded. Now, what you'll see immediately here is that we're talking about a long-term cycle here as opposed to a hydrologic cycle, which works pretty rapidly. Phosphorus cycle, we're talking about a span here of, hundreds of thousands, millions of years for the actual part of it that moves once it becomes rock. So how do we affect this? Well, there are two giant ways, and phosphates are really a controversial thing. We'll see when we talk about water quality later in the year. There are two main ways, and this seems like this is small because you're like, man, in nitrogen you had like 5 things listed here, and you've only got 2 from phosphates. But these are 2 enormous ways. So we've got runoff from fertilizer, and we've got household detergents. The fact of the matter is detergents work a lot better with phosphates in them. The phosphates help to get stuff clean a lot easier. There's some chemistry involved there that we're not going to get into right now. But the problem is that those phosphates don't dissolve all that well in water, but they do run off pretty well. So that means that a lot of household detergents have phosphates in them, and most fertilizers have phosphates in them too. And so that stuff is all going to run off. I mean, think about all the times that your washing machine, where does your washing machine put out its water to? Well, it puts it back into the city sewer system, or it puts it into your septic tank, where it's going to go down into the eventually down into the aquifer. In some way, all those phosphates are going to make it back into the system. And as phosphates, much like nitrates, when you get a lot of them into a water supply, since they're such a powerful nutrient, just like the nitrates are, they will also cause these giant algal blooms. I grew up in Central Florida, and a lot of our lakes were dying off through a process called eutrophication that we'll talk about again when we get a little bit further on this year. But that's basically that so many nutrients happen that you get these algal blooms that happen, and through all of that, it actually pulls out the oxygen and kills off all the other life that's in that lake.